Swayam Prabha. Digital India. Educated India.
Hello, welcome to another lecture. This is lecture 3. This is a pre-recorded lecture. Again, tomorrow we will have the live lecture. So I want to continue from where we had ended last time. So in the last lecture, we had been discussing a parallel plate waveguide. So parallel plate waveguide is like this. It extends to infinity because W is the width and D is the spacing between the plates. Now I had already discussed the TEM mode solution. Today I will state the TM mode. So for TM mode the solutions are, so these expressions are already given in the notes. So what are the important things to know? First, you see that h of z is 0. Okay, so there is no component of h along the z direction. Okay, next is that E is present on the ZY plane only. It is not, E is not present on the X plane, X direction, I beg your pardon. So if we can plot, the direction of H is this way, and E is on the ZY plane, so it will be like maybe like concentric ellipses. Okay. Okay, so this is how the shape of the wave is, and I just want to reiterate that the shape of the plane wave is something like this. Okay, so the shape of the wave changed from this to this, and in the process, this having a wavelength of say lambda g, and say this has a wavelength of lambda, then lambda g will be greater than lambda. Now why is this so? If we write the expression for, also note one more thing, that there is this constant n which I mentioned is an integer starting with 1 and going to infinity. So we have infinite. It appears as if we have infinite solutions, and it's true. Although how many might actually exist to be detected, that's a different matter. But yes, theoretically there are infinite number of solutions, and theoretically there are infinite waves present. So each of these modes, so each of these n, so n corresponds to what are known as modes. Okay, now each of these modes is a wave. It's an actual physical wave which can be filtered out to a different direction, or we can each of these is an individual wave, and all these modes can coexist together. And there was a question last time that what determines the modes that will be actually transmitting to the waveguide? It is determined by what is the source mode and and how you interface that mode to the waveguide. So in this case, for example, I can give a simple example. Suppose you want to transmit TM mode like this. One way to do it is simply connect another parallel plate waveguide which is also transmitting TM mode, and because you interconnected it at the end, it will simply continue transmitting that TM mode. So that is similarly, if you have this parallel plate waveguide transmitting only TE mode, and if you connect it like this, it will continue transmitting TE mode only. So that's how, so that's why, means what will actually be transmitted depends on what is the source and how you interface it. One other way of thinking of these modes is like they are gateways. So each of these mode is a gateway for transmitting power and information, and it's like which gate transmitting in a particular mode means you choose which particular gate you want to open. Now coming to the wavelength, or rather the beta. Now beta represents the spatial frequency of the wave mode. You see that each value of each mode will have a different value of Kc, and so beta will be different for each mode. Okay. And the wave guide or guide wavelength lambda g is given by 2 pi upon beta. Now k is given by omega square root of mu epsilon. Okay. K represents the value of beta 0 or the beta in free space. That is not through a waveguide. As you can see, because beta is lesser than beta 0, so lambda g will be greater than lambda. So that's the reason lambda, that's how mathematically you prove that lambda g, the guide wavelength, is larger than the free space wavelength. Now similar treatment can be done for the TE mode, and I would like you to go through the derivation for the TE mode. So with that, yeah, that's all about parallel plate waveguides. Now, one thing that I didn't mention here is that there's also something called a dominant mode. But dominant mode term, the mode that has the lowest cutoff frequency. Now, what is cutoff frequency? The concept of cutoff frequency comes from this equation. So for this to be beta to be real, for an electromagnetic wave to be propagating, beta has to be real. If beta is imaginary, then this this exponent becomes this term becomes real, and that this is real, then the wave will decay quickly. So for beta to, so the propagating electromagnetic wave can exist only when beta is real. For beta to be real, K should be greater than Kc. So in other words, omega square root of mu epsilon should be greater than n pi upon d. Okay. If we can show that the speed of light in free space is given by 1 upon mu epsilon, mu 0 epsilon 0, and if we assume that this is mu and epsilon correspond to free space, then we have, so this equation, if we expand this equation, so from this we have omega should be greater than n pi c over d. Okay. So this is, so from here we can write that 2 pi f should be greater than n pi c over d, from which we should be able to write that f is greater than n c over 2d. Okay, so fc, the cutoff frequency, is equal to nc over 2d. So this is the value of the cutoff frequency for a particular mode, and the concept of dominant mode that I mentioned is that the mode that has the lowest cutoff frequency doesn't arise in a parallel plate capacitor because it can transmit TEM mode, and TEM mode doesn't have any cutoff frequency. It can propagate for any frequency. So what it means is, so from this equation, this concept of cutoff frequency means that there is a frequency below which the TM or TE modes cannot exist. That is, no power or information can be carried below this cutoff frequency. This is one limitation of TE and TM modes. On the other hand, TEM mode can transmit over any frequency. But as I said, not all waveguides are two conductor waveguides, and for single conductor waveguides the transmission is possible only in terms of TE and TM. So let us see an example of a single conductor waveguide, which is the rectangular waveguide. So rectangular waveguide comprises of, it's like this. It's like, it's a hollow pipe actually. It's a hollow pipe with a broad edge, say A, and a narrower edge, say B. Okay. So here also, as I said, only the TE and TM modes will exist, and the value of the TM and TE modes are given. So let us say the TE mode for this H of Z is given as So this is the complete expression. This is available in the book by Posar. So you see that again Hz is present only. So here say again this is my Z, this is Y, this is the X direction. So Hz is present only, that is only H is present along the Z direction. E is present only along the XY plane. Okay, so only along this plane. And H of X, H is also present on the X and Y plane as well as in the Z direction. Now one other thing to, so this is for a rectangular waveguide. Now one other thing to note is that you see instead of a single integer constant, we have two integers m and n. So these are like so in other words, the modes that we have for the rectangular waveguide for the TE are of this form, x, y. So for the parallel plate waveguide, we had modes like TMX or TEX. For rectangular waveguide, we have modes in this form. And as I had mentioned in the last class, the rule of thumb is that the number of degrees of freedom you have, that determines the number of subscripts there is. Now the beta value will be similar to what we had for the parallel plate waveguide, which is okay. In this case, Kc and the cutoff frequency for a particular mode will be given like this. The value of Kc for that particular mode divided by, okay, so this is how I think I switched off the video, I think. Yeah, so this is the value of the cutoff frequency. Now coming to you might be wondering how we got this value of C equal to 1 upon mu epsilon. That comes from, remember in the first lecture I had mentioned about constant phase. Suppose if my phase is constant, and then if I differentiate both sides with respect to time, then I have then Vp omega upon k. Okay, so k, remember from Maxwell's law we can derive k. This is what is known as the wave number vector. For those who have taken E301, they know that k is the wave number vector, and the value of k is given as epsilon. So from this we have Vp is equal to omega upon omega square root of mu epsilon, which is equal to 1 upon mu epsilon, and this is equal to C for mu equal to mu 0 and epsilon equal to epsilon 0. So now we can, let me take a fresh page. Yeah, so we can now you saw that beta, which is given like this, Okay, so coming back to this curve, so here I have plotted two curves. One is this red line, which represents the omega versus beta variation in free space. Why am I saying this is free space? Because see here, the beta 0 is equal to omega omega mu epsilon. So this is equal to omega upon c. Okay, so you see that the relationship between beta 0 and omega is linear, and that is what it is actually. Here omega is equal to beta 0 c, but this line represents in waveguide. Now this shape will be same both for the parallel plate waveguide and the rectangular waveguide. This plot is for a particular mode, okay, and this omega c is for a particular mode. So for TE10 we will have a different mode. For TE11 we will have a different mode and a different graph. Okay. Now what is important you see is that this cutoff frequency, it ends here. Now the positive omega can always be positive, we cannot have negative frequency. So we find that there is a particular range of frequencies which is where they cannot transmit these waveguides for a particular mode, and these frequencies correspond to the frequencies that are below the cutoff frequency, and these are also known as forbidden frequency, or sometimes this this entire range is called electromagnetic band gap. Okay, so so I hope this is clear. What is electromagnetic band gap? So electromagnetic band gap is that range of frequencies where transmission for a particular mode is not possible. Now one more concept comes, the dominant mode, which I had discussed. Now for a waveguide, for a rectangular waveguide, because there is no TEM transmission possible, hence we do have the concept of dominant mode. For a parallel plate waveguide, we didn't have the concept of dominant mode because TEM mode was possible. So TEM mode is the dominant because it can transmit over all frequencies. Here for a rectangular waveguide, the dominant mode is TE10. Okay. So this TE10 has the lowest FC. Now I would urge you to do the complete derivation for the TM modes. Find out the values of the cutoff frequencies for the TE or for the various TE and TM modes, and indeed verify that TE10 has the lowest FC. I won't cover this, but I would also urge you to go to do the derivation for cylindrical waveguides. So cylindrical waveguides on your own, okay, and again find out all these values, and there you will find for a cylindrical waveguide, you'll find that the dominant mode is the TE11 mode. Now we also have the concepts of lambda g, the same, the guide wavelength that we discussed for the parallel plate capacitor. So lambda g will be given by 2 pi upon beta. Okay, that is the equation is same, and lambda g, again because beta is lesser than beta 0, lambda g will be greater than lambda in free space. And okay, so that was all about the electromagnetic properties of waveguides. Now this graph that we draw here is called the dispersion curve. Dispersion curve. Let me write it properly. Now, what do I mean by dispersion? What is the concept of dispersion? So dispersion brings back to the concept of group velocity and so group velocity Vg and phase velocity Vp. Let me take a fresh